Welcome to another video for Stat 212. In this video, we're going to continue with confidence intervals, but now we're going to talk about what we do for these estimation errors that we have to make, and we're using S in place of sigma, and how we're going to use what's called a T interval, a T confidence interval, instead of a Z interval in this context. So as a reminder, the issue and the assumption that we just kind of waved our hand at earlier, I don't know why this says chapter 8. This must be old. I think this should say chapter 6. Chapter 6. There's one important detail that we need to remember, and that is that when we're doing inference, it means that we're just using our sample information to try to make a claim about the population. However, we've just been kind of assuming that we can calculate the standard error of x bar exactly, meaning that we would have sigma, the population standard deviation. However, if we only have our sample information, then that means that we're only going to have S. We're only going to have our sample standard deviation instead. And this is going to be only an approximation of this standard error of x bar. We're just kind of, you could just call it kind of an estimated standard error in that context. So this creates a potential for some error in our process that we need to account for. And so we're going to use what's called a T distribution to do that. So what we did before, we usually call it a Z interval, and that is when we are kind of making a confidence interval, assuming that we have sigma known. If we don't have sigma known, though, then we're going to use something called a T interval. That's going to be a slightly wider interval than we would use otherwise. We're going to explain a little bit of why that's the case and how that kind of gets calculated in a very superficial way. Okay, so there's this thing called the T distribution. And the T distribution you might also think of as like a corrected normal distribution, or a normal distribution with fatter tails, which might sound a little bit silly, but that's really what it is. It's not the normal distribution, but it's still symmetric about the mean, and it's just going to be kind of stouter and wider at the tails. So you can kind of see these examples here. And the other thing that's weird about the T distribution is there's a bunch of them. There is a different T distribution for any particular sample size that we might have here, which is also just makes it more confusing. So a normal distribution, oops, well, I guess that kind of works. So a normal distribution has a particular shape. It is this bell shape that occurs naturally in a lot of contexts. It occurs when we're looking at sample statistics and how they're distributed a lot of the time. A T distribution is just a slightly corrected version. So whenever we don't have sigma, which is almost always the case when we're working with means, we estimate it with the sample standard deviation. We have that extra level of variability and uncertainty, so we're going to make our confidence interval slightly wider. So that's why we have this error correction, and we're going to stretch out slightly more distance than we would otherwise. So when we wanted a 95% confidence interval before, we could just stretch out 1.96 true standard errors away in either direction. So if we knew what the true standard error was, then we can stretch out 1.96 of those in either direction, and 95% of the time, that includes the parameter. However, if we had this estimated standard error, it could be off by a little bit. So if I stretch out 1.96 estimated standard errors, it may not work 95% of the time, because sometimes, about half the time, it's going to be too small, about half the time it's going to be too big, and that's going to end up kind of messing up the probabilistic claim a little bit, because if I want to be 95% confident, and half the time I underestimate and half the time I overestimate, I'm going to end up being a little bit less confident. I'm going to end up actually being more like 90, 92% confident. We're not going to kind of derive what that exact confidence is going to be for different sample sizes in this context, other than just kind of say it's a problem, that we will consistently make an interval that's a little bit too small too much of the time to make this work. So our answer here is to extend out just a little bit more to ensure that we are going to be 95% confident, that 95% of the time our interval does include the true mean if we're using this estimated standard error value in place. So there is going to be a t-value that we plug in instead of a z-value here. And that t-value is going to depend both on the confidence level we want as well as the sample size that we're working with, which is going to relate to this idea called degrees of freedom coming up here. So for example, so the t-value for 95% confidence is always going to be greater than 1.96. But that magnitude of difference depends on how large a sample size we have. So if my sample size is 15, that t-value is going to be 2.145. If n equals 50, it's going to be 2.01. And as n increases, t 95% is going to approach that 1.96 value closer and closer. The logic here is that the larger the sample size I have, the closer this value is to approximating this value. The more accurate my S value is going to be in estimating sigma. So that's why these t-values are going to eventually kind of converge toward 1.96 as my sample size gets larger and larger and larger, because I don't really need the error correction anymore if that's the case. Now, we'll talk about this more as the course goes on, but there's this thing called degrees of freedom. And we're not going to really explain why we use this in the context of t-distributions, other than just to say that if our sample size is 15, our degrees of freedom is going to be 14, and that's going to dictate which t-distribution we're working with and what the t-value we're plugging in is going to be. So it's more just kind of, this is the terminology that gets used in the context of t-distributions and t-values when we plug them into, say, a t-interval. Even though we're not really unpacking why this is important now, because if this is the only application of t-distributions, it would seem kind of unnecessary. But there is reasoning why this terminology is used around t-distributions, because there's also some more complex situations that we will actually see at least one example later in the course where this makes more sense. But there is context why we use this term and why we don't just relate the t-distribution we're working with directly to the sample size itself. So all you need to know is that when we're doing this one sample t-interval, we might use this term degrees of freedom, and it's always going to be our sample size minus 1 in this particular context. All right, so let's apply this. There's going to be a lot of similarity with what we've already done. We're just going to be using a t-interval now and highlight where these differences are going to occur. So here we have 57 patients who are considered representative of the high cholesterol population, over 50. They are trying a new medication for cholesterol. They had an average cholesterol drop of 27 milligrams per unit, deciliter, maybe, I don't remember, with a standard deviation of 18. So first, our assumptions met, assumptions met to create a confidence interval from U. And so remember, there's two things that we talked about. The first is our sample needs to be representative of the population it's supposed to represent. So representative, it appears that that is the case, at least that is stated here. So a lot of times with these kinds of problems, we're just going to state it and not worry about how it was collected. So we've already talked in the course about internal and external validity. So when we get to this point, we're just kind of assuming these things are okay and that there aren't a bunch of limitations, even though in real studies there always are limitations. So we're focused here on the procedure now, and we are assuming that we've learned this kind of design context, and later in the course towards the end we'll kind of put these things together a little bit more and critically evaluate all of these ideas at once. But for now, we're just going to kind of state it. The sample is representative, and we're going to check that box that we have met that condition. Number 2, can we assume the distribution of possible sample means for average cholesterol drop is normally distributed? And we only need one of these two conditions to be true. Number 1 is that the population is already fairly normal or symmetric. Number 2 is that our sample size is sufficiently large. So we don't really know anything about that first one, but we do know that n equals 57. And so barring a population distribution that's really skewed, this is probably okay. And I'm just going to say probably good unless pop distribution is very skewed. All right. So, but for our sake, we're just going to say it's okay. It meets our condition. Next, we're going to calculate the standard error for our sample mean and interpret what it means. So as you remember, the standard error for x bar would be sigma over the square root of n. However, we don't have sigma. Instead, as usual, we're going to have s, and we're going to have still n. And that's going to be 18 over the square root of 57. So how do we know that this isn't the population standard deviation in this context? Because we're describing our population, so notice this wording here. They had an average cholesterol drop of 27 with a standard deviation of 18. So that's kind of assuming this is a sample statistic. It is a measurement describing my sample. And if you think about it contextually here, why would I just randomly have sigma thrown in here? So in context, I can kind of read the statement and say this is a description of my sample. This is S. And therefore, I probably need a t-interval now to make a confidence interval if that's my goal. So this is going to come out to some value, 18 divided by the square root of 57. And I'm going to get 2.384. I changed colors. I guess I'll change back there. And interpret what this means. So that means that the expected error in x bar as an estimate of mu is 2.384. Now that's not a contextual description, that's just a very generic kind of interpretation there. So it's just saying a standard error is how much error we expect in our x bar value, or our sample statistic, as an estimate of the parameter it's representing. Our error could be more than that, our error could be less than that, but this is our best guess for what that error is going to be. Now we're going to find a 95% confidence interval for the average cholesterol drop of patients over 50 with high cholesterol. So we have our population, we have our population description, we have our sample information from 57 folks. Let's calculate this. X bar, our interval is going to be x bar plus or minus the appropriate t-value times the standard error of x bar. So again, this is kind of an approximate. I'll put a little tilde over it just as a reminder that this is our approximated standard error. That's why we're doing a t-interval, because it's an approximate standard error. So this is going to come out to be, what was it, 18? 27. 27 was our x bar. Plus or minus. Now this information is given, by the way, so that's nice. So we are not going to be using a t-table. We're not going to bother just going to R to find this value, because that's just not really important in this class. So in these contexts, when we're doing, say, a t-interval or a t-test, you will always be provided the appropriate t-value associated with this confidence level and this degrees of freedom. So our t-value is going to be, our t-value is going to be 1.997 times our standard error calculation of 2.384. My thing needs to catch up with me there. It's kind of odd. Okay. All right, so we're going to calculate this out. There we go. 27 minus 1.997 times 2.384. So my lower interval is going to be 22.24. My upper interval is going to be 31.76. Report the margin of error of our confidence interval. So that's going to be this distance from our point estimate to either edge. So I could do this one of two ways. I could just calculate this part. So this part is my margin of error. I could also just do 27 minus my lower bound, and that would also give me my margin of error, but it doesn't really matter here. 1.997 times 2.384 is 4.76. So again, that's just kind of helpful. So depending on how you're reporting this, you may not report the interval. You might instead report your point estimate and then state that the margin of error is some value for 95% confidence. Again, that's how a lot of polls do it, so both of those kind of reporting methods are common. If we had a patient over 50 with high cholesterol, could you use this interval to say that you are 95% sure his cholesterol drop would be between these two values? This is a great question for you to think about first. Based on everything that we've talked about with confidence intervals, is this an appropriate interpretation of a confidence interval, yes or no? So the answer here is no. Confidence intervals do not tell us about the position of individuals in this population. They tell us about where we believe the parameter is located. So confidence intervals cannot cannot is not the right word that I want to use. Do not indicate the position of individuals. The 95% range for individuals is going to be much, much wider than our confidence interval. There's probably going to be people who had a increase, a decrease, whatever. So that 95% range would be much, much bigger. It would be represented by the 1.96 standard deviation range, but not the 1.96 or approximate standard error range. So just keep that in mind. And then lastly, what kind of claim would you report from this finding? Is this medication effective on average? So notice that this wording here, is this medication effective on average? So we can't necessarily comment about individuals, but we can comment about this average result of did it seem to work on average? And if you notice, if our point estimate is 27, so they had an average cholesterol drop of 27, and you'll also notice that our interval is entirely contained above 0. So since our interval is entirely contained above 0, then we are at least 95% confident that mu is, and this gets a little bit, I guess, yeah, I'll say mu is above 0, where we're saying that the units for the measurement here is drop. So the drop is above 0, which might be a little bit confusing. Maybe we should think of it as negative in that case. But just to be very consistent with how I wrote it up until this point, the drop, we are 95% confident that there is at least some drop here, that this value is above 0, if that's how we're thinking about it. Now, if our interval straddled 0, that would be a different story. That would mean that 0 is still kind of in this plausibility range, that 95% that this 95% zone includes 0 as a possible parameter. But in this case, our interval is entirely above 0, meaning that it's pretty unlikely that mu is over there, because our information suggests that mu is somewhere in this range around our x bar. So if our interval contains 0, it's different. Then we couldn't say this with confidence. Then 0 would be a kind of a plausible candidate for the parameter in that case.